So, perfect. The floor is yours, Kenneth.
Okay, thank you, Dennis. Before I get started, I want to make sure that people are aware that the CernVM-FS development team is in the call as well. So Jacob, Laura, and Valentin are in here. So definitely, if you have any questions on CernVM-FS, today will be a good time to ask them, because we have the real experts in the call. Also, while I'm going through the slides, don't hesitate to interrupt me. Just raise your hand or shout if any questions pop up. So I'll start with EESSI a bit. I'll try to keep it short as well. So I won't do too much introduction. I think we all understand the issues where we're getting in a situation where there's too much software for a single support team to handle. We are definitely seeing that very well in Ghent. Our systems are different enough that we see different problems when installing the same software on different systems. So even though we have tools like EasyBuild and SPAC that help us quite a bit there, they're not really enough anymore. So we're still each installing our own software stack and each dealing with our own issues that are specific to our system. So there's a lot of duplicated work across HPC sites, also across scientists who are trying to get the software that they want to use to get it working. And as a result of that, we don't have a very uniform software stack across systems. We have a very diverse software stack. So some things are installed in some places or in different ways as well. The three pictures here kind of give a view of what the current situation is. On an HPC system, you typically have some kind of central software stack. On some systems, that's very extensive. On others, it's quite minimal. And then users do their own stuff on top of that, maybe manually compiling applications and libraries, or totally ignoring the central software stack even, rather than building on top of it. On their own desktop and laptop, they're doing the same thing, but probably in a different way. And typically in cloud, lots of people are using containers. That also happens locally and on HPC systems, but there's definitely caveats there, especially with large multi-node simulations, and of course when making sure, or when you want to make sure that your binaries are really optimized for the system that you're going to run on. So currently you are in a bit of a difficult situation, and going forward I only see things getting worse, especially when we're talking RISC-V CPUs, for example. All the container images we have now are essentially going to be useless. We'll have to start over again. So EESSI wants to try and give a solution to this situation where we build a shared software stack essentially, and where we don't cut corners on building binaries that work anywhere, but we still optimize the installations for particular types of CPUs, so we can use the full power of the machine. So that could help in making things a lot more uniform. You could have the same software stack on lots of different systems, HPC, laptops, cloud, and essentially use the exact same software environment across all these systems. So you get the feeling that you're running the same software stack everywhere. Underneath the covers, things may actually be different. So you'll get different installations when you're running on ARM or x86, for example. But to the end user, if they don't really care about that, they're not really exposed, thanks to some tricks we pulled in EESSI. So EESSI has a layered design. It has 3 layers, where the file system layer is essentially just CernVM-FS. So that's how we distribute the software stack across the world, essentially anyone who wants to use it. We have a compatibility layer that makes sure that the software applications we provide work on any Linux distribution. So we build our own glibc in here and shield ourselves away from the host operating system as much as we can. And then in the software layer, that's where the big software stack is installed and built. So we use EasyBuild for that. We give you environment modules that you can consume with lmod, and we have a small library that does CPU detection and picks the right part of the stack when you start using it. Across the board, we also use Reframe for testing all of this and making sure it works and keeps working. So this is, let's say, the general goal of the project, where we have some applications. In this case, these are the applications that we have in the MultiXscale Center of Excellence. We install them in the shared software stack in EESSI. And when EESSI is available on EuroHPC systems or cloud or laptops, you can just start using this software as if it were installed locally on the machine. So you're getting the same software stack everywhere, and any updates or any changes that are being applied to the software stack automatically stream to the EuroHPC systems or any systems that are making EESSI available. So to some extent, it's a one-time effort to make EESSI available, and then any updates that are being installed in that software stack automatically stream in. So you don't really have to babysit it too much. Towards an end user, that currently looks like this. So if EESSI is available on your system, we give you an initialization script as a part of the repository. You source that script, and that's all you need to do to update your environment and make the software installations that are part of EESSI available for use. So Espresso is one example here. You just load a module and you're good to start running. In the background, when you start running software, CernVM-FS will actually check if it already has those binaries and the necessary libraries to run that software. If it doesn't yet, it will automatically download it in the background from a mirror server, put it in a client cache locally on the system, and then actually start running it. So it's hiding the fact that it's not actually having the software installations locally on the system yet, but it pulls that in as needed if they're not available yet. And these mirror servers are fed by a central server. I'll get back to that later. So maybe a quick demo of that, and doing it interactively is always a bit more interesting. I'm on a system here in Ghent, a worker node, an Intel Cascade Lake worker node, where I've deliberately wiped the module path. So even though we have modules available here, now everything is essentially gone. That's just to make sure there's no mix-up.
Can you make that a little bit bigger?
Sure. All right. So the first step is assuming that EESSI is available, which it is already here on the system. So in this /CVM-FS software eeessi.io, that's where all the contents of the EESSI repository are located. And as a part of that, there is an init script for a particular version of EESSI. When we source this init script, a bunch of things happen. So first of all, our tool to detect what type of CPU you have will figure out that we're on a system that is compatible with an Intel Skylake architecture. So we don't have specific builds for Intel Cascade Lake, so it falls back to Intel Skylake in this case. And based on that, it knows which part of the software stack to use. So we split, it's essentially a collection of different subsets of installations optimized for specific CPUs. In this case, it picks the ones for Skylake, and it adds the path to the environment modules for those installations to our module path. And if we now do a module avail of, for example, Espresso, we will see that we have Espresso available for loading in this long path here. To show you that it also works, let's maybe load something we know a bit better than Espresso. So we'll load this PyTorch module. That may take some time. So if the information on which modules are available are not cached yet, CVM-FS will pull that in the background. But when that's done, we can start a Python session and we can import Torch, so the Torch module in here. Also, this part, again, may take some time. So any action you take that requires files which are not available yet on the system will have a small hiccup because CVM-FS is pulling those in the background. Now, they should only take a couple of seconds, hopefully. But if it does long, yeah, okay, there it goes. And if I check where this is coming from, I can see all of these files are coming from the EESSI repository here. Now, the good news is you get the same experience on any system where EESSI is available. You just source that script, you start loading modules, and you start using the software. And even if things are very different on the system itself, different CPUs, even ARM CPUs, the user experience is exactly the same. So you don't really have to tell much about your system. You just source that script and you hit the ground running. So a little bit more details on how that works, looking at the different layers. And this is the one we're going to focus on today because that's how we make EESSI available on different systems. On the file system layer, we're using CernVM-FS. And the EESSI setup here is the part in the middle where we have a central server, which is called the Stratum 0, which is a physical system in Groningen, University of Groningen in the Netherlands. This is where we add all the software installations that we want to make available publicly. So this is also the only location where a select number of people have write access to the repository. And then all the contents that are available here are automatically copied to mirror servers. So these have a full copy of everything that's included in the repository. Today, in the EESSI network, let's say we have 2 mirror servers, both in a cloud environment. We have one in AWS in Dublin. No, wait, this is Frankfurt, I think. One in AWS in Frankfurt, and one in Azure in the US East Coast. We can easily add additional mirror servers if there's a need for that, but currently we don't see a need yet. And we have a third Stratum 1 server, which is used for synchronizing your own private mirror server. So setting up your own mirror server does make sense, especially for bigger systems like HPC clusters. This is recommended. You don't have to do it to get access to EESSI, but it is definitely recommended to make sure that that automatic downloading of software that happens in the background can be done quickly. So you're not seeing big delays and starting to use software for the first time on a particular system. I'll get back to that because I have some performance startup benchmarks that we've done. As a single client system, so a laptop or a desktop, you're also getting access to those software installations via one of the public mirror servers, and CernVM-FS will automatically pick the closest one, so the one that should be giving the best download speeds for that software. There's also lots of caching going on, so once you start a software application once, it will be cached locally on the system where you were using that software, and it will not download it again and again from the mirror server. So CernVM-FS was really built for distributing software installations. It knows about all the quirks that are involved in that, small files or files that are related to each other. So it can do lots of things to make sure that goes fast and is all cached well. Okay, I'll give some more details on CernVM-FS, especially how to install it and how to configure it later in the talk. Then the compatibility layer, so the middle layer of the EESSI project is where we shield ourselves away from the operating system. So it's a small set of tools and libraries, mostly libraries, including glibc, for example. So that just makes sure that we don't need to care about which operating system is being used, whether that's a Red Hat-based or a Debian-based, SUSE-based system. We don't really care too much because we're not going to use the libraries that are provided by the operating system for the scientific applications that we'll be running. The compatibility layer also includes an installation of LMOD. So even if you don't have LMOD on your system yet, you can still consume all the modules that we have available in the EESSI repository. So the compatibility layer is also part of the EESSI repository. So that means these libraries are installed in this long, weird location, which is definitely out of the ordinary. And that's the reason why we're using Gentoo prefix. So Gentoo prefix is a sub-project of the Gentoo Linux Linux distribution, where you can install binaries and libraries from source, and you can pick where they are installed to. That's an important aspect. We need this because we need to be in the CVM-FS namespace. Then when we go to the actual applications on top of that, we're linking everything with our path to make sure we don't accidentally pick up the glibc from the host operating system. And by doing that, we can use the same installation. So in this case here, we're on an Intel Cascade Lake system that's running RHEL 8. But if I would be running Debian or Ubuntu here, the exact same binaries will be working fine because of that compatibility layer we have. And then the software layer on top. So that's where the bulk of the work is being done. So here we have optimized scientific applications like PyTorch, like Espresso, like OpenFOAM, and so on. We don't have one installation, but we have multiple ones even within a particular CPU family like x86-64. We'll have optimized installations for Intel Haswell systems, optimized installations for AMD Milan or Zen 3 systems, and so on. All of these installations are built with EasyBuild, so that's how we make sure things are optimized for those specific CPUs. And the user interface is through LMOD, through environment modules. And again, what's very important here in the software layer is that everything we build here must only be linking to the compatibility layer. If we break out of this, we have to be very careful that things keep working. There are some cases where we have to break out of it. I'll get back to that at the end. And like I show you, the host CPU is automatically detected. So here I never told it we were running an Intel CPU or anything more specific. It can do auto detection using a small library that we use. So that's a very high level on EESSI itself, how that all works. Now the part I think we're most interested in today is CernVM-FS. And just as a reminder here, I think most people here already know, but we had a tutorial best practices for CernVM-FS in HPC, which was done together with the CernVM-FS development team who are in the call here. It's a 3-hour tutorial that we held early December, which was also recorded and it's available on YouTube. Also, the slides are available, the website here, the tutorial website itself with all the contents, all the details, starting from scratch. So if you don't know what CernVM-FS is, we'll explain it to you here, what all the use cases and features are. We use EESSI here as an example repository, an example CernVM-FS repository. And then step by step, we explain you how to get access to CernVM-FS repositories using EESSI as an example, what you need to install, how you need to configure things, and so on. So the slides I have here are like a very summarized version of that tutorial. So essentially doing a 3-hour tutorial in, let's say, 20 minutes. So it is going to be very fast. But if you want to learn more about all the details or look at things at a slower pace, the tutorial is definitely the place to be. And again, if there's any questions, especially on the upcoming slides, do let us know because we have the CernVM-FS experts in the call here. So now's a very good time to ask. So step one, if you're interested in making EESSI available on your system, is to make sure that all the client systems, so typically the worker nodes, maybe also the login node of your HPC cluster have access to EESSI. There are actually a number of ways of doing that. The main one, the recommended one, is to have a native installation of CernVM-FS of the client. And for this, you really need admin rights. So you need to install packages and do some configuration and through /etc/CVM-FS. You also need to make sure that there's a CVM-FS user which has access to specific locations, like where the client cache will be installed or will be used. There's a couple of options here for where you put the client cache. By default, that will be in varlib CVM-FS. But if that's a problem or you don't want this, you can configure this to put it in RAM disk or even to put it on a shared file system like GPFS or Lustre. So these things are covered in the tutorial here. Configuration of HPC systems. So there's an in-memory client cache option, a loopback on a shared file system, an alien cache. So there's a bunch of options here, but they all come with caveats. So it's definitely recommended to have the client cache locally on the worker nodes, either on disk in varlib CVM-FS or another location, or in RAM disk if you can save the gigabytes in memory. So for more details, mostly look at the tutorial, but I have some details in the slides coming up as well. If for some reason you cannot or do not want to have a native installation of CernVM-FS, there are options, but then it definitely affects the user experience. And I'll try to show that hands-on. 2 particular options. So you can use a container image that you run via Singularity or Aptainer, where CernVM-FS is included in the container image itself. So you don't need it on the system to get access to EESSI. And another tool is CVM-FS exec, which pulls some tricks like user namespaces if they're available in the kernel that you're running, to also get access and to mount CernVM-FS repositories as an unprivileged user. And I'll try to show this on Minuxina, where EESSI is not available system-wide yet, or CernVM-FS is not available system-wide yet. So the native installation looks like this. So the commands basically fit on a slide. This is what you should be installing on a worker node. you install the CernVM-FS client software, which you can, there's an RPM here, for example, to get access to the CVM-FS repository, and then you can just yum install CVM-FS to get the client software. We recommend to also install an additional small package which adds some configuration files for CernVM-FS to get access to EESSI. So these will be put in /etc/CVM-FS. And then the other thing you should do is configure the CernVM-FS client a bit via a file like CVM-FS default.local, where in this case we're telling it two things. We're telling it there's the client profile as single, which essentially means we're not going to use a script proxy, but we're straight going to access the mirror servers. In this case, this is not really a production setup, but it's good enough to get access. And we limit CernVM-FS to use at maximum 10 gigabytes of disk space for its client cache. So the 10,000 here is 10,000 megabytes, 10 gigabytes. With that in place, we can run CVM-FS config setup, and that's enough to get access to the EESSI repository, as an example, to source that init script and start running it. So to show you how quick that can happen, I'll quickly launch a virtual machine here in AWS. I'll use Ubuntu as an operating system. I'll use ARM as a CPU architecture just to show you that it also works on ARM. I'll have 8 cores available. I'll have a key available, and I need to make sure I have enough disk space, even though I'm not really going to use anything more than 8 gigabytes. And I hit launch. Now this should launch in a couple of seconds, actually. At least it did this morning when I tested it. So this will give me a public IP address. Okay, and now I can switch to a terminal here, and let's see if this already works. It spins up very quickly. Right, so there it is already. So this is a Ubuntu system, so of course I cannot use the yum install commands I have in the slides. But in the EESSI documentation here, we do have the commands to do a native installation on a Debian-based Linux distribution. I can just copy this. It's going to essentially do the same things: install the CernVM-FS client software, install that configuration package for EESSI, create that configuration file for CernVM-FS to tell it that it cannot use more than 10 gigabytes, and then complete the setup. So I'll just copy paste this here and then get back to it. It will be done in a minute or two. And that's all you really need to do on a client system to get access. Of course, this is not a production setup, because here we're really relying on these mirror servers, like we're relying on these rather than having something close or in our network. So for a single client, this is good enough. But if you have 1,000 worker nodes in your HPC cluster, you definitely want to do a bit more, and I will get to that. All right. A small detail here: if you want to change the location of the client cache, it really boils down to adding a line like this in the configuration file. In this case, we're telling it, please use this directory in devshmem, so in RAM, and let's limit it in this case to 4 gigabytes of memory rather than 10, because 10 may be a bit much. So you can easily configure things a little bit differently beyond the defaults. All right, it's already done with installing those packages here, and that's enough to get access to the repository. And again, this was a totally new VM, totally empty, so nothing will be cached here, but it should be quite fast because in this case, I'm quite close to the mirror server that we have in AWS. So I can source the init script again, exactly the same way as I was before. I can check which software is available now. So you'll be seeing all those modules available from the EESSI repository. In this case, we're on an ARM system, so it's a Neoverse N1. But here I can also load the PyTorch module and get the same experience as an end user. I can check which Python I'm running. It will be coming from EESSI. I can start it. There may be a small hiccup when it needs to pull down those files again, but I can import Torch, and this should be working fine. And once this completes, I can show you where it's pulling in all that data in the cache as well. Okay, so that's working. When I check here var lib CVM-FS, so in here, this is really the location where it's pulling in all the files that are necessary to be able to run all that software. And I just want to show you how big that is. So right now it has downloaded about 400 megabytes of data. But again, this is a totally different system than the one I was on before. It's a Ubuntu OS, it's an ARM CPU, but I'm getting the exact same user experience. Okay, so if you can do a native installation, that's definitely recommended, but there are other ways. One way is using a container image that we have prepared, which we call a client container. It's available in the GitHub container registry. So for this, you need to do a little bit more than just start the container, because we need to mount the CernVM-FS repository when the container is launched. It really boils down to running these commands here. So we prepare some temporary directories that we can byte mount to var run CVM-FS and var lib CVM-FS in the container, because those need to be writable to download all those files. So for the CVM-FS client cache, we do a fuse mount of the software easy.io repository using the CVM-FS2 binary, and we tell it to mount that in /CVM-FS/software easy.io where it's expected. And when you do that, you should be able to access EESSI as well. Now let me do that here, which is a bit backwards because this system actually already has CernVM-FS available system-wide, but I can show you that just using these commands will start the container, and in the container we have access to the repository as well. So as an end user, as long as Aptane or Singularity are available, you don't really need to talk to your sysadmins if you just want to play around with EESSI. Now this is good enough for single node kind of work. For multi-node, that gets quite tricky very fast. So that's why we recommend having a native installation instead. So that's one way of accessing EESSI without having a system-wide CVM-FS installation. Another one, which is very interesting, is CVM-FS exec. So CVM-FS exec, I think, cannot potentially also use a container. So this pulls a whole bunch of tricks in the background. And the best way is to check a repository which mentions what it's going to use as tricks. So depending on the capabilities of the kernel, essentially, whether user namespaces are enabled or not, this will try a bunch of options, and the first thing that it tries that works is going to be good enough. So here, let me show this on Meluxina. So log out here, log into Meluxina. So the login nodes on Meluxina are very minimal. There's not even a module command available in here because they don't want users to run any calculations on the login nodes. So we won't get very far. But thanks to CVM-FS exec, we can actually get access to EESSI quite easily. So we clone the repository, we run the make dist tool that's available, and the CVM-FS exec repository. And what this will basically do is unpack CernVM-FS, the client software in here in this directory. And that's all we need to get access to the repository. So from that point on, you can run a command like this. So you use the CVM-FS exec binary, you tell it to get access to this CVM-FS repository. And then after the -- you can run any commands that use that repository. Here, I'll just start an interactive shell so I can show you what's going on, if that's working. Hold on, I messed that up. That wasn't doing what it should be doing. Let's do that again. So I'll trash this because I accidentally removed something. Doesn't take long, so I can do it again. Demos are bound to go wrong. Okay, so I run this, it loads. Okay, maybe it is available. Yeah, okay, it's actually there. So without having CVM-FS on the system or much of anything, I don't even have Aptane or Singularity here, I think. Yeah, it's not there on the login nodes, but I can still get access to EESSI, source the init script, and again, get the exact same experience as I did with a system-wide version. Now, again, this is good enough for single node stuff. Running multi-node workloads with this is going to be at least a bit tricky. You can probably make it work, but then you have to understand a bit of what's going on in the background, because every worker node will need a unique client cache directory, and now it's just caching things in here in varlib CernVM-FS, I think. Well, okay, the cache is in here somewhere, so it's all caching things locally. But when you're using multiple worker nodes, you need to be very careful with that. So there are options if you don't have a system-wide installation. So that was step one, getting access. Now, if you want to get a production setup, then you need to do a little bit more homework. You typically want a private mirror server here, like I mentioned before, in your own network, because you don't want to expose yourself to the latency of using a public mirror, which could be far away. But you also want to be a good citizen in the community and not hammer the mirror servers with thousands of worker nodes, because then things are going to slow down for everybody else. So that involves setting up one of these mirror servers, one of these Stratum 1 mirror servers in your own network. This is covered very well in the tutorial here. So how to set up your own, it's called replica server or mirror server. So that involves installing an additional package, CernVM-FS server, and then making sure you have the public key of the repository and some configuration as well installed. And another thing you'll need to do is to synchronize your mirror server with one of the public mirror servers, or in the case of EESSI, with the synchronization server we have available here. So you are responsible for making sure that your mirror server is up to date with everything that is going on in the repository. That's typically just a cron job that you set up and then probably forget about. But maybe you'll need to keep an eye on this a bit to make sure it keeps synchronizing and making sure it doesn't run out of disk space and so on. That's a little bit of homework there. Get back to the right slide here. So that's mostly relevant to improve the startup performance of software. If you don't have your own mirror server, things will be a bit slower. It also helps to make sure that things keep working, even if there's a connectivity issue to the outside world, either accidental or deliberate. So you can work around that by setting up your mirror server in your network. And you'll be syncing the contents of the repository via a sync server or a Stratum 1 that can serve as a sync server. And what I didn't mention here, it helps with offloading the mirror servers as well, the public ones, so they do not get hammered by thousands of worker nodes. In addition to that, you can consider setting up additional proxy servers as well, which I think is maybe shown in here. Yeah, so these are a collection of 6 or 7 mirror servers. So pretty much the same thing, but for the bigger sites, they also have proxy servers in front of those mirror servers, again, to offload the mirror servers and to make sure that things are not locking up because they're being hammered by lots of worker nodes. So even if you have your own Stratum, your own mirror server in your network, it may still be interesting to set up mirror servers, proxy servers, especially when you have thousands of worker nodes. A single mirror server is probably not gonna deal very well with that. But there are ways to scale that up and make sure everything keeps working well. So all the details on that are in the tutorial. I won't explain how to set up a mirror server or a proxy server. That quickly gets very technical and maybe not worth doing, but it was recorded in the tutorial session as well, and it has all the details there. Now, one thing to maybe drive this home a bit, why is it important? So I mentioned many reasons. One of the reasons is startup performance of software, and a very good test case of that is TensorFlow. So just doing an import of TensorFlow, we've benchmarked this and we've looked at all the details. This triggers over 3,500 open system calls and about 500 open dir system calls as well. So there's lots of metadata activity going on here just to do a single import of the TensorFlow Python package. In the background, and this is data we got through CernVM-FS, it requires almost 3,500 files. Over 2,000 of those come from TensorFlow itself, and most of those are small PyC files, so compiled Python modules. And then another about 1,000 files are coming from additional Python packages that are outside of the TensorFlow installation itself. So basically dependencies of TensorFlow that are required as well. In total, that's a little bit over 1 gigabyte of actual files that are needed on disk to be able to run this import TensorFlow. So we use this as a test case to look at startup performance of software. So that's really the first thing that happens in a lot of workloads. And we looked at various scenarios here. So first, we looked at some ground truths. So what kind of timings are we seeing if the full software stack is installed on local disk of the worker node, or even in RAM disk? Okay, RAM disk is not really realistic, but it does tell us how fast we can get in theory. If it's installed in RAM disk, we see about 2 seconds to run an import TensorFlow. If it's installed on local disk, local SSD, we're already increasing that to about 4 seconds. But that's, let's say, a realistic timing for an import TensorFlow in an ideal scenario. Then when we look at more realistic scenarios in an HPC setting, for example, NFS, so here we're actually not doing too bad. It's about 6 seconds. So compared to a local disk, this is doing quite good. But this was an NFS file system that was not really loaded at the time. So if your NFS file system is under a high load, things are going to look very different. So that's definitely something to keep in mind. So I think we all know that NFS doesn't really scale well with lots of load. But then looking at production shared file systems where many people have their software stack installed on. Lustre is one example. So these are benchmarks of a tier 1 system in the Flemish Supercomputing Center, which we have in Ghent. If you're starting cold, so where TensorFlow has not been run recently and the file system cache does not have any of these files, you're getting about 80 seconds to do an import TensorFlow. And your Lustre file system can definitely be tuned to improve this a bit, but you need to be careful that you're not tuning it for only using software and not using any big I/O workload. So it's very difficult to tune your file system that does well in different scenarios. If it is cached, so if everything is in the kernel file system cache, then we're around 3 seconds, and then we're doing quite good. We're very close to what's optimal. So for Lustre, starting cold is a big issue. We did the same thing for GPFS, and things are a bit worse here. Well, okay, starting cold, it's about 40 seconds. So it looks like our GPFS file system on our tier 2 clusters is maybe a bit better than Lustre. But what's more scary is that even if you have hot caches, so hot GPFS caches, you're still getting about 30 seconds for an import TensorFlow. We looked at that closely, and that's because some of the GPFS caches are a bit too small to catch all those tiny files. So there's a stat cache, which I think had about 1,000 entries. And we need 3,500 files for TensorFlow. So it was really hammering that stat cache quite heavily. We could change the configuration here. That would help a lot. But then again, we have to be careful that we're not overloading the GPFS metadata servers and all of that. So this is a somewhat realistic experience, I would say. Then if we look at accessing TensorFlow via CernVM-FS instead, so in this case, we were using the EESSI repository. First of all, if we look at the cold situation where we have cold kernel and CernVM-FS client caches, we looked at different scenarios. So using the public mirror servers that we have in EESSI, if we rely on the one in the EU, then we're hitting about 50 seconds, okay, a little bit more. So let's say between 50 and 100 seconds. So that's not terribly good, but we are pulling the data from a server in Frankfurt while we are located in Ghent. So that's not very surprising. If we push that to the extreme and we force CernVM-FS to use the mirror server in the US East, then of course we're getting about 5 minutes of wait time before that import TensorFlow completes for the first time. But if we do have a private Stratum 1, so a private mirror server in our network, then we're seeing only about 10 seconds. So as long as it doesn't have to go outside of the network to get the data, things can be quite fast. And with the private proxy, that gets a little bit better, also a private proxy in the network. So this already on the cold start end, as long as you did your homework, already looks quite a bit better than Lustre and GPFS. and when the client caches are hot, or when the kernel cache is hot. So hot cache is when everything is already cached by the kernel, then we're very close to the optimal scenario. If the kernel cache is cold, so the files are not in there yet, but they are in the CernVM-FS client cache, then we have the other scenarios, and then we're seeing startup times of a couple of seconds. So as long as it's been cached on local disk already, or in RAM disk here in this case, then of course we're getting very good startup times. So this just shows the importance, mainly here, of having a mirror server in your network if you want to make sure your startup performance is okay. And it also shows that it's possible to do better than what we see with GPFS in a cold scenario, and same thing with Lustre. So that really shows that CVM-FS is really tuned or targeted towards providing software stacks, even on big systems. Now, there's a lot of caveats here. This was a single node test. CVM-FS was not really hammered quite a lot because not many people were using it. So there's a bit more homework to do here to really make this, to understand this a bit better. But there are some very good signs here that this could be a good solution. All right. Do we have any questions until now? Because I know some people have to leave at 11. I do have some more things to cover, if not.
Yeah, maybe I have a question regarding the compatibility layer. So for the different EuroHPC systems, we would also need to have optimized bindings. So for specific MPI versions or maybe GPU bindings, how can we integrate that?
Yeah, that was my next slide actually.
So. Perfect.
Yeah. Well, I only have one slide on this, not a lot of details, but I can explain the idea a bit. So we are very aware that sometimes you need to break out of this compatibility layer and use stuff from the host operating system. One prime example of that is GPU drivers, for example. So we are not going to install GPU drivers in the EESSI repository itself. Those really have to come from the host operating system. And what we're doing here, and this is well covered in the documentation, is that we have some scripting to expose the GPU driver libraries to EESSI. So if there's any GPU software available in EESSI, that you can run that with the drivers that you have in the OS. So I'm not sure I can click through the details here a bit, but this is really covered in detail here. The trick that we use is we have, as a part of the EESSI repository, we have this directory. It's actually a symlink called host injections. And by default, this will point to opt-EESSI. But this is not a regular symlink. It's what's called a variant symlink in CernVM-FS. So that basically means that you can configure CernVM-FS to point it to a different location. So you're in full control over what this symlink points to. And for example, I'm not sure where that's specified, how to configure that. I guess we're just pointing to the documentation.
It was just below where you were, Kenneth. And so just underneath it says EC hosted, that there, exactly there. Yeah. That's in the configuration file.
Yeah, okay. So if you put this in your configuration file, this will determine what this path points to. So you can determine that. And that gives us a location where we can write stuff in. So even though this repository is read-only, because we have a symlink that can point to a path where, well, typically a sysadmin can write things into, you can inject things, libraries into the EESSI namespace, essentially. Now, we're using this for GPUs. So we have a script here that will find the GPU driver libraries in your host operating system and then put symlinks in that host injections directory. And if you do that, I'm not sure we have the details on that here. I don't think we have a good example, but when you run that script, you will see that it populates the host injections directory with symlinks into the operating system. And essentially, when you have a vendor MPI, so an MPI library that your vendor tells you, please use this and don't try to use something else to get good performance, you can use the same trick. So you can symlink those libraries in host injections, and they will be automatically picked up by the binaries that we have in EESSI. And that is something I can show. I can even show it here. So let me source things so I have a binary to look at in a bash. Let me load PyTorch. So what I want to show you is that that host injections location, it's something that we bake into every binary that we include in EESSI. So if I do a read elf -d on the Python binary that we have, you will see the RPath section, which is going to be quite long. But one path in here, I know the host injections is only there for MPI stuff, right?
Yeah, I was just about to say we restrict that to right now to just MPI.
Okay, let's see. I need something MPI.
You could pick Quantum Espresso or something there.
Okay, this one need to purge first. And here, I guess, what am I looking at?
Yeah, pw.x is the.
Right, so if you check the RPath section here, you'll see this host injections path that's always baked in. So any libraries that are being put in there will be picked up first and will win over anything that that is provided in EESSI itself. You're in control over replacing particular libraries. Of course, those libraries have to be ABI compatible with what we built against. So there are some caveats there, but you definitely can do that. And also for the GPU driver libraries that are necessary, even though we don't provide them in the EESSI software stack, as long as they're available through this, they will be picked up and they will be working for the binaries that need them. Does that answer your question, Dennis?
Yes, thank you.
Yeah, so we're very aware of this. We're prepared for this as well. We can probably improve this a bit. The vendor MPI aspect is currently not in our documentation, but it's very similar to the GPU situation. And this is something that we've tested. Remind me, Alan, we tested this with EFA and AWS, right?
Yeah, EFA, because that's the only thing that they support, right? The one that they ship, right? So in their case,
the Elastic Fabric adapters, so they're equivalent to InfiniBand.
Yeah, you have to use what they ship.
Yeah, and that was working fine. So we got.
I mean, it's not zero effort. I mean, there's a little bit to do to make that work exactly because you're using the runtime linker from EESSI, so that has an impact as well. But it's a solvable problem.
Yeah. And we were testing that with GROMACS, and we were indeed seeing an improvement in performance, right?
Yeah, it was not enormous, but it was measurable. It was 10% or something like that.
Okay, so that's one thing. Okay, that's specific to EESSI. That has little to do with CVM-FS. That's more, let's say, internal organization of the EESSI repository, but that is an important aspect. And then the rest of the slides I have are looking at use cases. This is mostly repetition. But if there's no native CernVM-FS installation, you do have a couple of options. I showed two of them, using a container, using CVM-FS exec. There's other ways as well. There's an alien cache where you can prefetch the cache that CVM-FS needs, put that on a shared file system, and then let CVM-FS use that instead. So if you don't want to have you don't want to have a cache on your clients, that's possible, but then you need to manage this yourself. So CernVM-FS will basically not touch this or not do any garbage collection. You're in control of synchronizing that. That's both good and bad in some sense. There's other tools as well, like shrink-wrap, which can from a CernVM-FS repository create a container image. So as long as you have some place where you have CVM-FS available, you can create a container image and basically handpick the parts of the repository you want, get a container image from that, and then run it like this. And once you have the container image, you don't need CVM-FS at all anymore.
It's not a container image. I mean, it's a squash.fs.
Or squash.fs image. Yeah. So all of these come with limitations, and yeah, you may need a bit more experience to run these. So the user experience is less smooth than with a native installation. But there definitely are options here, and especially running multi-node workloads with a setup like this, it gets tricky very fast. So then you need to be very careful. But it is part of our tutorial as well, so we do mention all these options. In the case of diskless worker nodes, I already mentioned these. You can put the client cache in RAM, and actually just a couple of gigabytes is usually sufficient. You can also put the client cache on the shared file system through a loopback file system, where you essentially have a directory per worker node on the shared file system that will work. But then you're exposed again to the downsides of GPFS and Lustre and those latency issues. So that's definitely something to be aware of. And an alien cache here is also an option, but there's downsides there as well. And then with offline worker nodes, which is in the case of Mare Nostrum, for example, this is relevant. As long as you have your private mirror server in your network, so this guy here, then your worker nodes only really need to talk to the mirror server or a proxy that's in front of that. So the worker nodes don't need access to the outside world. You do need, on your mirror server, you do need to synchronize that with something that's available through the internet. So that part would be online. There's no direct connection from the worker nodes to the outside world in that sense. But that's something to be aware of. Now, there is a scenario here, or a possibility here, that you've set up 2 mirror servers, and when you're synchronizing them, you're making sure that the worker nodes are not using them, for example. So if you want to make sure your worker nodes have no way, absolutely no way of accessing the internet through that mirror server, then you can do a setup like this, which is a bit more involved, but it really depends on how strict you want to be. And when that mirror server is being synchronized with the public network is entirely under your control. So you need to run a CernVM-FS server snapshot command to pull in the updates from the repository. So that's up to you. Okay, I have a slide here as well on how we're adding software to EESSI. That's an important aspect. There's a whole workflow here, which I maybe won't explain in detail. The important thing here is that we make EESSI a community project. So we let people outside of the project propose additions to the software layer by making a pull request and with under human review, let's say. So we will not blindly accept things. What's also important is that everything is being built from source. So we're not just taking binaries that people give us, but we're building them from source. Also because we want to optimize them for the different CPUs that we have. So that's automated through a build bot, which is running currently in AWS and building for each of these supported CPUs. We have a testing step in there as well. So it's not because we get the binaries that we blindly assume that they will work anywhere. So eventually we will test those in different scenarios, in different operating systems, but even eventually also building software on AWS and testing it in Azure. And only if that works, we'll claim it's good enough to be included in EESSI. And when we get those installations, which come in the form of tarbals outside of the build cluster, they eventually can get added to the mirror server, to the central server, sorry. And also there we do that under human review. So that's not fully automatic, but with a human approval step in between. All more details on that are available in the EESSI documentation. And yeah, another slide here to wrap up, but I guess it's clear, and a bunch of links to click on if you need more information. So that was the condensed version, let's say, of the tutorial. And maybe we still have time for questions, if there are any questions.
Hi, thanks, Kenneth, for the tutorial. It was really nice. I mean, to see it again. Just here, from I would say a point of view of this current project, the CI/CD project, for basically the COEs to promote their software within the EESSI, they have to follow basically the workflow that you just mentioned, right?
Yeah, that would be the idea. That would be the idea, that they get the software installed through this mechanism.
Okay.
So right now, that means supporting the software first in EasyBuild, because that's the tool we're using to install everything. But in some sense, we're not restricted to EasyBuild here. It doesn't have to be EasyBuild if that's a problem. The restriction that we have is we need to make sure we only pick up stuff from the compatibility layer.
Yeah, of course.
And EasyBuild has a bunch of features for that makes it as easy as it can. If you're using any other tool, and that tool could be a simple bash script that you use to do the compilation, you just have to make very sure that it's using RPOT linking and it's only picking up stuff from the compatibility layer. But if that works, then we could accept any type of build procedure if that's needed.
Yeah, I think that's the caveat, right? It would need to be as safe, secure as what we have already implemented, right, within our workflows.
So there's a whole bunch of tricks we pull in EasyBuild to not only make sure that we're using RPOT and using the compatibility layer, but also like sanity checks left and right to make sure there's no surprises there. So that's the preferred way. But if that's a big hurdle or a make or break situation, yeah, then we can consider diverting from that.
No, it's just that from I would say this project point of view, I mean, especially from the COE perspective, because it seems that it's hard for everyone to agree on a CI/CD. Some will basically some hosting entity will provide Jacamar or whatever, and yeah, I mean, most of the hosting are running EasyBuild anyway. So yeah, no, just that how the different pieces of the puzzle come together is just something that yeah, maybe it's unclear for both the COEs and the hosting entities. I mean, I see all the pieces, and yeah, for us, at least in terms of hosting entities, the idea is to spend less time providing more software to our users, which are hand-tuned, fine-tuned for the specific architecture, and for that, it's definitely a win. I mean, I've played with Easy before; it's quite nice. I have to agree. And now, yeah, it's how to put the other pieces onto the puzzle to make the nice picture, basically, and convince the COEs to go there.
Yeah. So maybe something to mention there, this workflow is what we're currently using for the software.easy.io repository, which is the production repository. Now, if we're talking in the real CI scenario, we could set up a separate repository where the workflow is a bit different and maybe more automated, where you could, for example, for specific commits, trigger a build fully automatically and get it fully automatically deployed in the CI.easy.io repository. But then that would be a bit more access controlled in some other way, like we wouldn't accept builds from that by random people. So we have to know who is going on. So some kind of authentication mechanism. And that's maybe where Jacamar CI also comes in. So I think there's a combination possible of both Jacamar CI and Easy. They serve different purposes.
Yeah, definitely. Yeah, I see them. I would say forming a longer pipeline, but for serving more software. No, I just taking the COE perspective and how basically we put all the things that together to basically ease the suffering of everyone. Okay, fine. Okay, good.
Another question, Branislav?
Thank you. Can you hear me? Okay.
Yes.
Yeah, thank you very much for a very interesting talk. Where can we get the slides? Can we get the slides?
I will send them to Dennis, and Dennis can forward them to everyone. Yeah.
Okay, please do. This may help us to really get off the ground.
Okay. So for Carolina, Easy is already available on Carolina system-wide.
Okay.
So we were in touch with Carolina early on through the MultiXscale COE.
Okay.
And that's together with Vega, that's one of the systems where one of the EuroHPC systems where Easy is already available.
Okay, perfect. But still would be good to good
Yeah,
to have
sure.
this, because then we can build the documentation and this kind of things around.
Yeah. So one thing that we've noticed is the Carolina documentation still talks about the easy pilot repository, which is something we had until, let's say, summer of last year. But now that I think this should still be updated to use the software easy IO production.
What I can really recommend, and that would be absolutely great, it's very easy to contribute to the Carolina documentation.
Yeah, to send a pull request, yes. Yeah.
It's just a call request and merge request. So if you do that, you can easily make sure that this is up to date on Carolina, because this may be kind of a little bit beyond scope of what the people maintaining the documentations do.
Yeah. Okay.
So it would be really good if you find time for it.
Yeah, we're happy to do that and include some kind of example in there as well. So
yeah, that would be fantastic.
Get a feeling. Yeah. Okay. Any other questions, comments, ideas? So Dennis had to leave at 11, Alan, I think. So I think it's up to us to wrap up the session.
Yeah, I just wanted to circle back to what Francesco said about the CI/CD stuff. I mean, what's really in this picture right now is the delivery part, right? So getting the CD part done, and then the CI part is, like Kenneth said, it needs a slightly different design, and we need to introduce some additional capabilities to do that. It's something that we're thinking about a lot. I mean, because we're obviously going to offer it as a service within MultiXscale. But it is something that we're thinking quite a bit about at the moment. And then if that's it, then I'll stop the recording now, and then